Okay, so good morning, everyone. And I'm Shambo, Assistant Professor in Mechatronics Engineering from Kali University, Jaipur. And uh, I've been working in the field of mostly signal processing or data pre-processing for machine learning data. And while working on it, I came across many uh, algorithms that require, like for data pre-processing or for that signal processing, what we do for machine learning. We often require these machine learning algorithms for processing those data itself. Okay, so initially I'll talk a little bit about the different signal processing or data processing techniques that we do for pre-processing of the data, and we will just discuss that how it is important to actually required why the signal processing or data pre-processing is required for neural network or machine learning algorithms. Okay, so moving ahead, this is our topic. So initially, I'll talk a little bit about signal processing and machine learning, that how I came into this field working, and then we will take machine learning for noise removal. We will talk for image processing mostly in detail. Okay, and we will also have a brief discussion how we can use this for other signals as well. And another main my topic involves is using statistical approaches for blind calibration or machine learning approaches. So if you know machine learning in details, these machine learning are mostly all statistical tools that we're using in layers after layers, thereby creating a series of statistical approach or to achieve some nonlinear regression or nonlinear classification tools. Okay, so moving ahead with signal processing for machine learning, we'll start. These are the basic, the basic steps that we use. That is this feature extraction, mathematical operations, and obviously the noise removal. Okay, so noise removal goes parallelly, but first we mostly we do feature extraction and noise removal in parallel, and then we do some mathematical operations. The mathematical operations that we generally come across are the, you can say, the moving average that we do, and the normalization techniques that we do. And why are these important? I think most of you would say, if you're talking about normalization, why do we need a normalization? Is suppose we are talking about the price of a, we are talking about the predictor for predicting house prices. Okay, and we in one feature we have room size or building area for the, yeah, the room size or the building size, and on the other hand we are having another feature, say number of rooms. So while the room size would be dealing from a size from say 1,000, 2,000, 4,000, 5,000 square feet, the number of room would be only having 1 to 10. Okay, and when we are entering those data directly into a neural network or machine learning algorithm, okay, what would happen is there whenever we are putting up some weightage to any of them, obviously the value which is getting multiplied with 1,000 and 2,000 or all those would always have a more effect rather than the number of room size, whereas so thereby subduing the size of that the impact of that particular feature. Okay, so for that reason, these mathematical operations are always required for pre-processing the data. Okay, so because the overall result from the machine learning would be depending on the data that we are providing, and then obviously we have this feature extraction technique, and where we either do statistical approach or we do spatial transformation. Okay, and for again explaining this, I would take up an example. Like when I came for my master's thesis, I was working on a project where it was sponsored by Tata Motors, and they have supplied us some lubricant oil. Okay, and we were supposed to determine the quality of those lubricant oil. Okay, and for that, what we did was we did some impedance spectroscopy of that oil, and some of the physical characteristics of the oil was given provided by the Tata Motors themselves. And what we need to do was whether we need to classify whether the oil was good or bad, okay, based on the physical properties that was given to us. Now, when we are using those impedance spectroscopy directly to neural network, okay, we expected that we have heard at that time we were new to this neural network and machine learning. So we thought that okay, neural network is a great machine, and if we all we need to do is we need to get the data, we need to feed it to the neural network, and voila, it would give some great result. It would give some great output. And obviously, when we tested the data, when we were training the data, okay, we get a very good prediction approximation, say up to 90-95% of accuracy, okay. But when we tried to cross validate or when we tried on the testing data, the result was very disappointing, and the accuracy was lesser than say around 60% or 65%, okay. And why was that happening was when we when we viewed the data, okay, when we are visually observing those, analyzing those data with number of features, we have seen that most of those data were uh, very random. Okay, and what neural network was doing when we were increasing to achieve better training results, what we were doing was we were increasing the non-linearity of the algorithm, and then we were changing the layers of the algorithm of the neural network so that we can get more better training results. But what ultimately it was doing, because of the all the random arrangement of the data, uh, the main problem was it was overfitting the data. Okay. Otherwise, if we are going for training lower training accuracy, then it was underfitting the data. Okay. So then we started to learn that what this neural network is actually doing. Okay. And then we realized that these neural networks are nothing but these are mathematical blocks. Okay. And we are doing a series of mathematical operation on it. So obviously, if we are not providing them a proper data, then it becomes very difficult for the neural network or the machine learning algorithm to incorporate a proper algorithm to weightage to this all these new layers and to get a good test result as well as a train result. So one of the feature extraction, most common kind of feature extraction in statistical approach is principal component analysis. Okay, and we straight away did this, and I would say that the result almost improved by, and we got a satisfactory result of almost 85 to 90% in even in training data. Okay. Now, what principal component analysis do is it would uh, it would do some again it would do some statistical analysis on the data, and based on the covariance of the data, it would transform the data set based on the set of data where we have highest number or say arranged as per the covariance or the variance of the data. For example, this image is again taken from this particular image is okay. So this particular image is taken from Wikipedia. You can easily, whenever you search for PC, you will get this image from Wikipedia. Okay, here we see that this data is pretty much random in nature. Okay, if we see it's been distributed in x and y direction in, we can say, in equal manner. Okay, so if we straightforward feed it in x and y direction, it will be very difficult for the predictor to predict anything from it. But if we check its variance, we can see that it's having more variance in this particular direction and very less variance in this particular direction. Okay, so if we transform this data into this particular uh, data format, in this particular axis format, then we can say that we can definitely going to have more kind of more accurate data. And moreover, what this sorry, what this PCA does is it helps in reducing the number of dimensionality in the uh, data that we are providing, the number of features that we are providing to the neural network, that we can reduce. And what helps in that is it helps in reducing the computational complexity in the neural network, because the number of layers, the number of the batch size is reducing. Okay, and obviously another thing is whenever we are reducing, we are partially removing some kind of and let's say obnoxious data from the data set. For example, again, if we suppose we come back to that example of predicting house prices. Okay, when we are predicting house prices, suppose we are using the uh, the features of, say, the number of rooms, okay, room size, and the locality. Okay, and we can from our general perception, we can say that the room size and the locality is enough for if we plot the data in this 3 dimension, we would see that the most of the variance would be based on the locality and the size of the building, the size of the flat. Okay, and the number of rooms plays a very lesser impact on that particular feature. So so based on that, if you are feeding all three data to a neural network, the result that we would get would be almost similar if we place in only the room size and the locality. Okay, because those are the two main factors which generally affect the price of the room, the price of the flat. Moreover, suppose in some of our examples, suppose in some flat, what they have done is though they have some small room size, some small area, okay, but what they do is they incorporate lots of rooms. Say in 1,000 square feet flat, they have incorporated 10 rooms, okay, because maybe their purpose was something different, whatever it is. But those kind of data is again going to give an wrong impact on the training of the neural network, okay? Because in general, the room size and the overall number of rooms would be somewhere proportional, right? So those kind of data also. So if we can, if we again do some PCA and we see that we are using the most data which are having most number of variants, the most amount of variants, then those data can be actually give you much better result in when you're incorporating this machine learning and those data into a machine learning algorithm. Okay, so this is kind of an statistical data. Second kind of data are the feature extraction through spatial transformation. One kind of spatial transformation is obviously the physical property based domain transformation. For example, obviously this includes all the methodologies that we generally learn in a signal and system classes, like we do Fourier transform, we can do Laplace transform, we can do wavelet transform, okay, or we can take up many of those other physical spatial transformations to extract feature from signals. Okay, so suppose if we are dealing with an audio signal, and in that audio signal, we know that our voice is going to range between this particular frequency range. Yeah, so if we can do an FFT and we can crop out all the data, all the other noises from those, the higher and the lower frequencies from those particular data, and then again do an inverse Fourier transform and get back to our time domain, we will get a much more better noise free data. So these kind of spatial transformation also helps us in getting features which are more useful in uh, giving a data which would be helpful for the machine learning. Okay, so generally because I work in this particular area, that's so that my data that is reaching to machine learning uh, can be actually helping the algorithm to provide such kind of a result or a better kind of a result. Okay, another kind of spatial transformation is color to grayscale. This I think anybody who is working in image processing would be using it, because most of the filtration and all those things, those algorithm works in grayscale images. Another transformation is from RGB to other, like as we can see in this particular, image, this image, that we can transfer this RGB to all those kind of, and we can see that the spatial domain for this, all these, so basically all these dotted lines are the axis that we are talking about. Okay, and these we can see that the whole spatial domain changes, and we can I'm this also I have experienced in my practical work when I was working in some live project. Okay, there we were working with some invisible ink, and whenever we give some uh, we project some UV light on it, we get an image which is uh, uh, we get to see that ink, and we need to predict what is written over there with that ink. Okay, so the if a problem we were having was whenever we were using two different camera, all their RGB values that there because of the compression and all those things, whatever they were giving was different. So what we tried was we tried to shift towards these other properties, and we have seen that in many cases two different camera, even though they are giving different RGB values, their HSV values are almost similar, or their other values are almost similar. So those kind of thing is what we can do. And again, the problem was when we are printing that is in CMYK format, and when seeing in an image that is in RGB format. So if we are again we can use these kind of transformation, we can get a more accurate data from the image that we are dealing with. Okay, so these kind of transformation also helps in getting a better result from the data, from the neural network. Okay, so I really want to emphasize on over this fact that we should we should have we must be doing all these kind of data processing before feeding that data into a neural network or any kind of machine learning algorithm. Now, in nowadays, if you go for some library, what they do is like most of the libraries naturally do their batch normalization. They goes for normalization. They do some feature extraction as well. They do this PCA and all those things, and they do uh, extract features, and then they feed into the. So these kind of layers are already included in nowadays libraries. But since those libraries are not totally in our control, we don't know what exactly the features they are providing, whether that is required or not. With some of our important features are getting omitted or not. So for that, doing some this important feature extraction prior to giving that data to feeding that data to the algorithm is very much important to us, okay, to ensure an better result from the network. And finally, the third part of this particular signal processing for machine learning topic is the noise removal. Now, as you can see in this particular image, that this image is nothing but combination of two sinusoidal data corrupted by a zero mean random noise. Okay, not even a deviated random noise, the zero mean random noise. And the signal was a simple two sinusoidal data signal combined together. And but from this data, we can never guess that this was a two sinusoidal data that is combined because of the noise that has been incorporated in this particular signal, right? So for this reason, it is very necessary, it is very important to remove this kind of noise from the data before feeding this data into neural network to get an proper result from that neural network, to expect a proper result from that neural network. If we're not doing this, then actually we are not we do not expect, we cannot expect a proper result from the machine learning data. Okay, so I will move forward with what are the kind of uh, noise removal technique that we can have with an example of EEG signal. So I'll be taking example of this particular literature review that was published in IEEE. Okay, and so for EEG signals, for noise, removal of noise from EEG signals, in general, they would most classic techniques is to use independent component analysis, and then manually they analyze those independent components, and then remove out the other not required independent components, and then we can use this. So this, but often when we are doing this ICA, we can only ICA can discard many other useful informations as well. Okay, so for that, with time, what they did was they combined. So again, now as I was saying, that suppose you feed this EEG signal directly to a neural network. Okay, what they would do is they would do a simple ICA, okay, because that is the most generalistic and the classic method. Okay, and then they would feed that data to the neural network. But it has been seen that if you're manually doing it and if you're doing a simple ICA, then many useful data also get discarded from that particular set of data that we are providing. Okay, and for that there are other algorithms that they combine with ICA to generate a proper to generate the proper data set. For example, they do factor analysis. Factor analysis is again it's based on variance, covariance based data. Then we have multivariate empirical mode decomposition. This is also a very generalistic approach that often been incorporated in nowadays CNN networks. Because before feeding into the CNN networks, they often goes to because this multivariate empirical mode decomposition is actually a very common method whenever we are dealing with dynamic data. Okay, a time-based data. Whenever we are going, we deal with those kind of data. This is EMD and common approach that is often been used for feature extraction. Okay, then obviously again these statistical approaches like joint approximation, diagonalization of eigen matrices again. So that also brings out the independent components of a particular data. Okay, the independent variables in a particular data. Okay, and then all these kind of use of covariance matrices and their related properties are also been used with ICA to find out the proper to remove artifacts from the EEG signal. Now, just those who are new to this EEG signals, the artifacts are like the noise that comes in. Obviously, there is due to the electrical signals. Okay, the sensors and all those electrical noises are there. Other than that, there are noises like whenever we blink our eyes, whenever we move our eyes. Okay, or suppose those who, from whom the EEG signal was connected, suppose he was getting some other kind of sensation. Suppose there was some burning sensation. Suppose there was some itching sensation, and we can see that for every signal there are different kind of artifacts, and we need to remove. So going through a single process or going through a single feature extraction method is not always very useful to actually obtain these to remove these noises. So we often go through this combination of statistical approaches. Okay, and then there are wavelet independent component analysis. Okay, so again there is a combination of wavelet based features. So we extract this wavelet based features. Wavelet is again a type of frequency domain transformation. Okay, which is used for dynamic data, which is more so FFT, the Fourier transform is more effective for static data. Wavelet is more so effective for dynamic data. Okay, and then we perform this ICA, and then we remove the artifacts from the overall signal. Okay, so this is the basic approach when we use this automatic ICA, and mostly this particular approach was initially done manually. But in general, when people are getting more and more EEG signal, more and more artifacts into the signal, it's become very difficult to do this manually, manually identify which are the independent components that links to our particular data. Okay, so in that case, what we do, we we use these classifiers to identify these artifacts. Okay, features like peak, entropy, the kurtosis value from the signal. Okay, the kurtosis value, entropy, and peaks are collected from the time domain signal itself, and then obviously from wavelet also we can find out the peaks and all those things. Okay, to take those features and use in classifiers to find out that EEG signal. So and it has been reviewed in that particular paper that people have used this normalized stochastic least mean square algorithms to actually find out a different kind of EEG signals and different noises, different artifacts in EEG signals, and to help to remove them as well. Okay, not only to identify but to remove them or to obtain clean EEG signals. Okay, so these signals, these features are used, these algorithms are used to remove and clean the EEG signal so that we can feed in a proper EEG signal to the sensor, to the neural network or the machine learning algorithm so that it can do its classification, do its job of classification or regression proper way. Okay, so so as we can see that the previously these kind of physical EEG signals and this physical transformation based features or the simple statistical features were not quite sufficient to clean out all the data because there were a lot of random nature in the artifacts that we were receiving. Okay, and for that people have generally slowly, gradually moved these machine learning algorithms or these more uh, you can say repetitive algorithms, statistical approaches with repetitive modes of cross validation and training and testing. Okay, so for that, now we move on to the main topic of machine learning for noise removal. Okay, how this machine learning are used for noise removal, and we'll take up this example of image processing, one of the paper that used machine learning CNN for image processing for removing impulse noise from the image processing. Okay, so impulse noise are basically whenever a pixel get damaged, okay, because of a certain burst of noise, okay, like we have the salt and pepper noises, okay, where the pixel gets totally white or get totally black. Okay, so those are the impulse noises, and to improve the quality of the images, we often need to remove those impulse noises. Okay, again, I would say that if you go into the CNN's algorithms that we are using, the libraries those we are using, okay, from in those are available in Python and other computing languages, you would see that most of the places they would be going through these median filters and age preserving these kind of algorithms to filter out the noises and to filter out these kind of noises. Now, the main problem with these kind of noises are they use with uh, these kind of algorithms are they are being used for all pixels, and with this when we are using for all the pixels, even the good pixels, so in that case we are actually reducing the information those are there which are being carried in the useful the good pixels are also getting damaged. Okay, so for these reasons, intelligent algorithms such as fuzzy network and SVM has been introduced in earlier stages, and later we are using neural network-based noise filtration to achieve better performance over traditional approaches. Okay, so and how this process works is we will follow this particular publication from of by Lingai Jin. Okay, that is learning deep CNN for impulse noise removal in images, and has been published in Journal of Visual Communication and Images Presentation. Okay, so basically the model that is used for the total process that is being used is shown in this particular figure. So the noisy image is being fed to the classifier network. So what this classifier network does is it tries to find out whether a pixel is whether the pixel whether the whether the pixel is good or bad. And if the pixel is say good, then it would label it as 1, and if the pixel is bad, it would label it as 0. Okay, so we would get an image. Okay, we would get the same. Suppose our image is an uh, say 100 cross 100 image. Okay, so in that case, our here we would get a matrix sorry. So we get a matrix. We get a matrix of similar size. Okay, we will get a matrix. We will get a matrix of dimension 100 cross 100 cross 100. I'm sorry, there's some problem with the screen. Okay, and which is having the value. So the matrix would look like 0, 1, 0, 0. So it would contain only the values of the 0, 0, and the size would be 100 cross 100. Okay, so this kind of matrix we would be getting in this predicted level. Okay, and this matrix would be then be mixed with this particular image. Okay, this particular image, and based on that we would be getting an image. So what it would do is, I'll go to right. So this labeling is done as 1 and 0. Then the image is temporarily modified by replacing those noisy pixels. Okay, whichever pixel value which is 1 in this particular matrix would be giving would be replaced by 0 pixel value. Okay, so we were having this we were obviously being feeding in a grayscale image. Okay, so we were having different gray values for this particular for each of these pixel, and which of the any of the pixel which is having a noisy signal, which is being labeled as a noisy signal, we are replacing that particular values with 0. Okay, so that is what the classifier is doing. It is first classifying the pixels. Okay, and then it is then replacing in this sparse clean image. Finally, when we are getting this sparse clean image, in that particular image it has replaced all the noisy pixels with a value of with a grayscale value of 0. Okay, and then we are having another network, another CNN based network, which is actually regressing with the noisy image. With the noisy image, it is regressing with the noisy image. Okay, uh, so it is replacing with the noisy image, and then it is regressing with the noisy image, and with the sparse clean image, it is trying to restore the original image. Okay, so that is what we are doing, and whenever for training, what we are doing is we are feeding in artificially labeled noisy images. Okay, for training. So what we are what the authors have done is they have used a very a standard set of images. Okay, then they have introduced some noises to particular pixels. Okay, and those pixels what they're doing is they have those pixels are then labeled as 1 and 0 as per the pixel, and those are used for classifying the network. So typically this is an supervised classifier network, where it is using an artificially noised labeled data, okay, to train the classifier. Okay, so that is what this image and this algorithm is trying to achieve. So this algorithm, the classifier, you can see that initially they have this convolution, they are using CNN. Okay, so so the first layer is they are using a combination of a convolution unit and a regularized linear unit, linearizing unit. Okay, ReLU we can see. Okay, and then also the last one is also an the last layer is also an only an convolution unit. Okay, so we have only convolution unit in the last layer. The first layer is a combination of convolution unit and a ReLU unit, and in between these layers, the in between layers are actually So the first layer, this one, okay, this is L1, and this is, say, if we are having the depth of BC, then I'm sorry. So this is the first one. This is for the classifier layer. Okay, this is for the classifier algorithm or the classifier network. So this is layer one. Okay, and then we have over here is the, if our depth is say DC, this is depth for the classifier, then the DC -1, that layer has only a convolution layer, convolution unit. Okay, a 3 cross 3 convolution unit is used for all the layers, and in between, this is what modified when we are when the authors were testing the data. Okay, so these layers were very, but the number of this layer was changed. Okay, and each of these layer was repeatedly, so in between, these layers are all of same type, but the number of layers were changed for optimizing the size of the network. Okay, to verify which network gives the most optimized result. And here we can see that they are using convolution, uh, convolution plus, I can say they are having this that is regularized linear units. Okay, and then obviously they are having this BN, this is batch normalized. Okay, and the authors have tried with both these batch normalized units and with non-batch normalized units, and they have seen that the batch normalized units are giving much better result as compared to the I'm sorry, as compared to the non-batch normalized units. So they have used these batch normalized units for a better result. And finally, this layer, the softmax layer is doing the classification, and this layer is doing the classification. Sorry for all the. So we have this classification. Okay, and this classification is basically saying that if their data is a 0 or a 1, if it is a 0 or a 1. Okay. Okay, so this particular data is providing that if it is a zero comma, it is softmax data or the softmax layer. Yeah. Okay, so this is for the classifier algorithm or the classifier network, and then obviously this particular label data. So this data, the last black and white that we are getting over here, this one is the label data. Okay, this is the label data that is coming, and based on this label data, the other picture, so here we can see that that label data is used with this sparse clean, this noisy image to generate this particular sparse clean image. Okay, and this sparse clean image along with the noisy data, along with the noisy image, is then fed to the uh, regression network. Okay, the regression network has a similar structure as the main the classifier network as well. Okay, the first one is it's having a convolution plus ReLU network, and then in between it was having convolution, a repetition of convolution plus normalized plus ReLU network. Okay, and then finally it's having only a convolution network. Okay, and the size of this each of these layers, the number of units in each of these layers were determined based on the picture images that they are using, the size of the patches they were using. So mostly, I think they used a 40 cross 40 patch size, okay, of image. And in each of the images, the percentage of damaged pixels were around was varied from 5 to 60 in a gap of 5. So they have 12 different so say it is having a batch of image batch of 40 plus 40. Okay, and in between that, so with that batch, we have created 12 different samples. Okay, one is having a noisy sample of a noisy pixel of 5%, the other one 10%, then 15, then 20, and so on to 60. So they have total 12 different uh, images samples they have created from a particular image patch. Okay, and those patches were then used in the classifier, and then finally to identify the to train the classifier to find out what to train that which of the pixels are to be called as noisy pixel and which are not to be called as a noisy pixel. And then in the regression, they also use those the normal kind of editing, the filtration that they do, that like mean filtration of the testing algorithm uh, to regenerate this particular proper better image. Okay, so I'm sorry, this is so yeah. Okay, so for result analysis, what they did was they used this false alarm ratio. Okay, and they use this false alarm ratio is the number of wrongly identified noisy pixels among all the pixels. Okay, false detection ratio is the number of falsely identified uh, noisy pixels among non-noisy pixels, and misdetection ratio is the opposite, is the vice versa of that. That is number of falsely detected non-noisy data, okay, or noise-free pixels as which was actually being a noisy pixel. Okay, so these three criteria was used, and it was seen that the algorithm was compared with two other. One was a normal neural network based, and another was SVM based. These classifiers they have used, and they have seen that the given this particular data, this particular algorithm was performing, though in some, I think for SVM the FAR was a little bit better, but for other two it was almost this particular algorithm gave much better result than the SVM or algorithm or the NN neural network based algorithm. Okay, and depth and percentage of the noisy pixels were varied during the training. Okay, and depth of the network, okay, depth of the network was varied, and the percentage of noisy pixels were very varied for training. Okay, and depth of the classification network was optimized to 18. Okay, that DC that I was saying, and DN for DR for the regression data, that DC and DR was for the DC for the DC, the depth for the classifier was identified as 18. Okay, that was the most optimized data, because after that the amount of reduction is FDR, MDR, and FDR was not that clean. So then for regression peak, the peak signal noise PSNR was calculated. That is the peak signal to noise ratio. Okay, and again for that that PSNR was compared with general standard, and it was seen that the 64 was optimized data depth for the regression network. Okay, and they got an overall mostly as the results go, they got an PSNR of optimized PSNR of 42. Okay. So for 60, the average for all those for 12 different noises. Okay, for noisy images. Okay, so they got an in batch normalized and non-batch normalized. Okay, so this was so we have seen that how these neural networks are now being used for noise reduction. Okay, so we have started with noise reduction techniques for feeding into neural networks or machine learning. Now we are seeing that, because so this shows that the importance of this, why people are working on this particular field, that why do we need to use these new algorithms for uh, getting for feeding the network with better data. Okay, so this comes another technique that we will be talking about briefly, very briefly, closing on the time. So uh, the next is blind calibration. So my current research almost revolves around this. Now, what is a blind calibration is now since we are talking a lot about IoTs, we are involving lots and lots of sensors in networks. Okay, uh, and we are also for the last 1 hour almost we are talking about uh, the quality of data that we are feeding into for processing and all those things. So whenever we are using sensor data, we must ensure that the sensor is giving a proper data. Okay, suppose it's 20 degrees Celsius and the sensor is giving an output of 50 degrees Celsius because of wrong calibration, then it's of no use, right? It doesn't give any meaning. It doesn't state any meaning to the, it gives any meaning to the network. It would be working on based on 50 degrees Celsius, whereas our original data is only 20 degrees Celsius. So calibration of these sensors are very important because lot of result or a lot of AI, our life is getting more and more involved with these sensor data, more dependent on these sensor data. Okay, so we need to have a good calibrated sensor data to be processed for proper applications. Now, for calibration of this data, for calibration of this sensor data in multiple sensor networks, it is not possible to every time go to all the sensors, check what is the ground truth, or give a reference signal to that, and do the calibration for that particular sensor data. Okay? It's not possible to roam around for, especially for mobile sensor network, remote sensor networks where people a lot of now army and military operations are going on where they incorporate all these wireless sensors in the border areas or the unmanned areas. Okay, and they're using this remote sensor network. Now it is not possible to every time to go to all those because they are risky zones. Okay, and they are also remotely located zones. So it is not possible to every time go and check whether the sensors are properly working or not, or and to calibrate those sensors with some reference data. Okay, and give that. So these are obviously very resource intensive task of dealing with this. Another kind of data that which requires is blind calibration are the gas sensor networks. Okay, gas sensor networks, more problem with gas sensor networks are their sensor selectivity. The selectivity of these gas sensors are not that premier. Okay, and they generally get affected by lots of gases. So it's not always possible to uh, check to calibrate them for all those gases for which it's sensitive. Okay, so for these kind of networks, for these kind of sensor data, we need an algorithm where it does not require a reference data to be calibrated. Okay, and for that we use this blind calibration or self calibration technique for uh, calibrating the data. Okay, and what it does is it utilizes neighboring or the redundant sensor data to calibrate instead of reference data. Now, when we are talking about sensor networks, the advantage that we are having is suppose in a locality there are 50 other sensors as well, which are collecting the data, same data. Okay, for example, if you know that uh, the Google Map, they gave this the Google Map gave this traffic data using the GPS data of our mobile. Okay, they are somehow collecting some data, there's some GPS data from the mobile. Okay, and now there are hundreds of mobile in a particular locality. Okay, and if some one of the sensor, one of the mobiles GPS is not working or not giving proper data, then what it can do is it can calibrate that sensor based on other data, other GPS data that it is getting from other mobiles at the same time. Okay, so in based on that, that is the kind of techniques that we use in blind calibration. Okay, rather than using a reference data. So in most so for blind calibration, this algebraic and statistical approaches. So Again, I would like to say that this optimization of machine learning algorithms, okay, what these algorithms are different from algebraic or statistical approaches are they are in these in the second approach. What they do is they learn continuously, or they regress over a certain amount of time. They go for those all those batch kind of learning where with time it optimizes its algorithm, its weight and everything. Okay, but for algebraic or statistical, they also go. They have a similar approach, but they go for a more batch wise regression, you can say. Okay, so for example, if you are using a mathematical equation, what it would do is it would do a mathematical equation and use that particular mathematical equation for calibrating the data. Okay, so it would generate that mathematical equation for the current batch, and then it would give the calibrated data based on that. What machine learning or optimization techniques do is they use the previous data and they go through this repeated process of doing it. Okay, so the basic approach remains same, that the sensor responses are collected, okay, from multiple sensors, that is measuring a similar phenomena. Okay, suppose we are talking about temperature sensor or light sensor. So what they would do, it would be working on all these different, it would be collecting the sensor response where y would be collected from all the sensors around within the locality, that is measuring the same phenomena. Okay, and then it goes through the calibration algorithm, and finally we will be obtaining this calibrated data x dash. Okay, in this particular equation that is given, that is y equal to dx plus n. Now again, this so y is the sensor response that we are getting, x is the original phenomena or the original data or the ground truth that we can say, d is the drift, okay, or the change in calibration, and n is the noise that is being incorporated. So the sensor response that we are getting is actually the drift within the sensor that has already occurred, multiplied with the original value of that original phenomena that has been measured, okay, and plus the n, that is the noise that has been incorporated within the sensor response. Okay, so these y are what we are collecting from the sensors. Then it goes to the calibration data, and finally we get a calibrated data, that is x prime, okay, or x dash, and then we compare with x dash with x, so that we can get more closer to x. This will be our main target, is to get an x prime or x dash which is more close to x. Okay, that is, and mostly these are, since there are a number of sensors, all these y and x and d and n are all vectors. D is a matrix. D would be the noise matrix. Okay, and in most cases it would be diagonal matrix, but or sparse kind of a matrix. But in gas sensors, if we are connected in a given shared data acquisition network, okay, then it would this D might not be a sparse matrix. So in these algebraic and statistical approaches, what they do is uh, they would in general be accompanying, they would be assuming that these D matrix or the N matrix have some proper properties like sparsity or redundancy, or a proper, it follows the D or N proper a proper uh, distribution like Gaussian distribution or some uniform distribution it would be following. And based on those assumptions, you cannot very false also, but always those are not always true as well. Okay, but they often give a much better result than non-calibrated data. That I would say. So if you're not using any of these blind calibration units, then at least you can go with this algebraic and statistical approaches. These are very less computationally intensive approaches. Okay, and all you need to do is to write this matrix manipulation codes, and then you can get it embedded in any simple processor as well. It can be done in simple processor, and the best part of it, these can be used for real time. Okay, the main problem with optimization or machine learning or neural networks are there, because of the lag or the indefiniteness of the result that we would be obtaining. Okay, uh, those are not cannot be quite suggestible for real-time operations, but this more algebraic or statistical operations can definitely be used for real-time operations. So that is a very important benefit of algebraic or statistical approaches. And because I was working for a real-time system, I opted for these algebraic and statistical approaches for blind calibration of gas sensors. Okay, and but while doing that kind of research, I obviously came across many algorithms for optimization and machine learning approaches. Now, one of this is a paper that I was currently reviewing was using a support vector regression algorithm for estimating coefficients. And these kind of use, obviously, it's a very good nonlinear regression tool. Okay, so it was used. So it was trying to generate this particular y equal to dx plus n. So it would be trying to calculate the D matrix and the N matrix, or the inverse of these matrices rather. Okay, so that they get the value of x prime over there. Okay, so this was used, and other than that, it was also combined with estimation algorithm. It was using state estimation algorithms as well to estimate next state. So it was using the current sensor responses, okay, the current sensor responses from the neighborhood, as well as it is using the previous sensor data to estimate the next state. Okay, and what it was doing, the basic concept over here was uh, what they were trying to do was so all the sensor data that it was getting, all the sensor data that it was getting. So first it was having an estimator. Okay, so it was having an estimator. Sorry for all the other. So the signal was coming, the previous signal. Okay, and it was having the estimator. So the current previous states were there, and finally it was giving out the current state output. Okay, and then this current state was checked with the sensor responses, all the other sensor responses. Okay, all the other sensor responses, and based on that, if it was checking whether the current value matches with all the other responses as well, and based on that, this it was giving a feedback to the estimator to change its whatever the estimator function they were using. They were changing the coefficient of that estimator so that it can give a more calibrated data over the non-calibrated data. So this was kind of an, so this was other local sensors or the neighboring sensors that it was using. Sensors. Okay, and here also it was getting previous data as well as the current data, and it was getting a feedback from these local sensors that whether this, and that way it was modulating its estimator to give an more calibrated data over here. Okay, so this kind of, so here we can see again they are not using a any reference signal. Okay, so what was happening was so the basic disadvantage over here is, since we are taking these local sensors, since we are taking these local sensors as the reference sensors, okay, so we hope that all these sensors doesn't go. So, and in practical, this doesn't happen that all the sensors go have a similar kind of a drift or a similar kind of a noise in. So because mostly these drifts are they're random and have a zero mean. So the overall average of these all the sensors, neighboring sensors, are expected to have an error of zero mean. Okay, so based on that, this estimator is being tested. Similar kind of thing was done for my experiment as well. I was working on uh, gas sensors, and in that gas sensor chamber, we were having actually a repeated positioning of a similar kind of sensor. Okay, so we gathered data. Since we didn't have time for having the drift in the sensor, so we simulated some kind of drift. Okay, we simulated the drift. So we had this gas sensor network. Okay, we had this gas sensor network with multiple gas sensors of same kind. So since this chamber was having a same gas was introduced to it, so we expected all the sensors to give a similar kind of an response, right? Though there are variants, that is other aspect we won't go into detail, but in general we will be expecting that the gas has been evenly distributed, and we are expecting a proper similar kind of response from all these gas sensors. Okay, and then we want these gas sensors to be uh, calibrated as well, because the gas sensors, we are working with conducting polymer gas sensors, and these conducting polymer gas sensors often come with the basic problem of drift. Okay, they get a random drift with a very high amplitude. Okay, so what my our task was, or my task was, we didn't have the time to see what kind of drift, original drift it was having. So what we did was we incorporated that wide Gaussian. We have used this particular kind of we used an random this drift matrix over there, and plus n, and we generated this y output. Okay, we generated this y response, and then we used an proper algebraic equation following a work done by Balzano et al. Okay, to find out this calibration, to perform this blind calibration, and we have got an X dash which was almost 90 to 95% similar, and we have tried it with various kinds of gas. We have tried with ethanol, methanol, then amine. Okay, so and combination of these two gases, we have tried with those features as well, and we have seen that the system almost performs up to 90 to 95 kind of. So this blind calibration using of machine learning for this kind of algorithm for repetitive checking and all those things are a prime can be taken forward as a prime research topic. Next. Okay, so thank you very much. That's all from my side. In summary, we have seen that the signal processing is an important factor to provide the prediction network of an optimized data network and optimized data, but in many cases, processing the data itself requires machine learning algorithm to be implemented. ML helps to obtain this kind of complex calibration matrices or equations to denoise the data set. Okay, so now I'll be giving you the mic so that I'll stop the sharing.
Thank you so much, Shambo sir, for giving such a wonderful lecture. You have given so much, you have given insights about signal processing techniques and what kind of algorithm we should use. Like if we have a weak signal, like especially in the biomedical field. So that was really a very nice lecture. So now I request all the participants, if you have any doubt, you can ask Shambo sir.
Yeah, the mic. You can unmute yourself if you have any question, and you can put it up. Otherwise, you can also put in chat as well. And as you know, we will be sharing the feedback and the attendance list as well soon after this session. So for this session in the chat as well as in WhatsApp group. Yeah, for if there is any question from anyone.
Okay, if there is no questions, then I'll post the attendance link and the feedback link to the in the chat section and also in the WhatsApp group. So I request everyone to fill that. So and then next session we'll have at 11:30. So I request everyone to please join that session on time. Thank you all.
Thank you so much.